Hello, my name's James Cash. Welcome to my talk for Clojure North 2020. My talk entitled Don't Stop Now, and what I'm going to do is talk a bit about learning new things and why I think it always behooves us to just not be satisfied with where we're at now. Keep trying to push our boundaries, learn new things, look at existing things from a new light. So, presumably everyone here is here because they like using Clojure. I know I do. And I think the reason a lot of us like Clojure is because it's a really powerful language. You know, it can do a lot. We probably came to Clojure from other languages that in some ways were lacking, you know, not quite as powerful, missing some things that Clojure gives us. And you know, Clojure is a really powerful language. It does give us a lot of things that other languages are lacking, or maybe not quite as nice. So Clojure is very powerful, but and my claim here is that it's not necessarily the peak of power. It may be a local maxima, but I don't think it's a global maxima. There may not even really be a global maxima in terms of programming languages, but that's maybe another discussion. The point being, I think that we can find things that can actually improve on the power that we have in Clojure, help us write better code more easily. Before we get into this though, we need to kind of discuss a little bit what do we mean when we talk about power in this context. You know, it's a thing that can mean different things to different people in different contexts, so to kind of, so we're starting from the same place. I'm going to talk, when I think about power in terms of programming language, the thing that I think it means to me, really, a big part of it is being declarative. It's about being able to express the solution to the problem we have in kind of the most direct, straightforward way that we can. I think maybe another way of thinking about it is as minimizing accidental complexity. So I kind of got this phrase from the seminal paper, Out of the Tar Pit, where we discuss the idea of we have essential complexity, which is the complexity that is maybe reflected by the actual complexity of the problem in the world that we're trying to solve. So maybe we have a complex solution, but if the problem itself is complex, then that complexity may just be necessary to accurately reflect the problem that we have. The thing that we want to try to avoid is this accidental complexity, this complexity that arises because of this impedance mismatch between, you know, the problem that we have, the solution that we want to develop, and the language that we have to use to express our solution. You know, the difference between we have this platonic ideal that exists in our head, and we have to communicate it through this kind of imperfect medium. And there can be issues with that, right? There's some things that are more awkward to express. What we want to try to do is minimize that. We want to try to make it as straightforward to express our solution as we can. So I think Clojure's power comes from a couple different things. So in, you know, no particular order, I think we have first-class functions are a really useful thing. I think at this point they're a thing that maybe we kind of start to take for granted because many languages have them. You know, even Java now has like lambdas. You know, for a long time, if you wanted to do something that the most natural solution, we want to reach for first-class functions. In Java, we were forced to do things like make anonymous inner classes and weird stuff like that. You know, in C, we don't really have first-class functions. You can have function pointers, but it's not as easy to just make a function. And so languages that lack first-class functions in an easy way, they make a lot of solutions maybe harder to express. The most natural solution to something involves having some little reified bit of behavior, some action that we want to pass around and do things with and store and kind of manipulate freely. If we can't really do that with functions, then it can make a lot of things unnatural. You know, it introduces friction. So first-class functions, I think, you know, is worth thinking of as a source of power. I think destructuring is another thing that's really powerful. Kind of this, like, you know, talking about declarative, I think destructuring is a very declarative way of doing common operations. You know, I don't want to have to, you know, talk about indices or remember exactly the keys and have a bunch of boilerplate code or to say, no, this equals that, this equals that, this equals that. It's much nicer to be able to say, here's kind of the shape of the variables I want and just match it with the data, and if things are in the right shape, I kind of get all the values I want. I think it's a really, like, it's a simple thing. It's not a thing that dramatically changes what kind of algorithms you write, but it's one of these little things that, because of the way it simplifies the code, it makes it, I just find it makes things easier to express, right? And I think we can see that it is becoming a more popular thing. It's a thing that I think a lot of the ML families have had for a long time, but you can see modern language, or other modern languages like JavaScript has kind of started to adopt that. Swift has similar things, so I think it's a very powerful idea that is becoming more widespread. Immutability, I think, is an interesting one to talk about the power of Clojure, because it's, in some ways, we can gain power by taking things away, by saying that things cannot mutate. Also have these very specific interfaces for doing so. It gives us power in the sense that it lets us not have to worry about a whole set of things. In so many languages, we have to worry, okay, and pass this data around, does it get mutated? Does this function call return the new value, or does it mutate the old value in place? Does it do both? Like, trying to keep track of it. If I pass this to a recursive function, is this thing going to change it? Or do I need to make a copy each time? Just to be safe, I'm going to make copies everywhere. What in this case, I don't want to copy. It's mutability, I think, just introduces a whole set of complexities and headaches that by having immutability be a core part of the language, again, just really simplifies how we can think about our solutions to problems. Of course, though, talking about power in programming languages, if we're talking about a Lisp, really the core of it, if we need to do something, we always have macros, right? Those are one of the big sources of the power of Clojure, or any Lisp family language. The fact that we can change the language itself as we see fit, right? People that program in other languages, if they want a new feature, they want something to change, they're forced to resort to kind of extra language things like preprocessors like Babel, or doing things in like XML, all these like various ways they have forced to add on. But if we program in a Lisp, we can say, what, I can change the language, right? There may be some kind of drawbacks to that. It may lead to a culture where people don't value pushing the language itself forward, because what you have is good enough, can you just build your own 90% solution? But it is undoubtedly like a huge source of the power of Clojure, that we can just change the language itself. We don't need to use it often, but when you do need it, there's not really any substitute for it. So macros are obviously a huge part of the kind of underlying power of the language. So Clojure's great. We have all these nice things, but then where do we go next, right? I think that, one, I just like learning new programming languages, but I think in general, we always should be trying to look, what's next? What can we do to make things better than they are now? We always should be, trying to look forward. How can we improve things? So one thing that I've been looking at recently that I've really enjoyed doing, and I think has given me kind of a couple new ways of looking at things, is Prolog. So people may have heard of Prolog. Usually the kind of a little file card is, it's a logic programming language. The context that a lot of people see it in is, it's for doing genealogy charts or something. It's a language where you say, X is father, and then Y is mother, and then you can say father Y, and it tells you who Y is the father of, or whatever. Like these kind of toy problems for doing, syllogisms or something. And, can be kind of do some neat things with that. And, there's things like core.logic, implementing mini Cameron for doing these kind of simple little logic puzzles. But, how is that interesting for actually programming on real things? And so my experience with Prolog has actually been that it's a really good general purpose programming language. A lot of it has to do with some of these interesting aspects of it being a logic programming language. And so kind of one of the first things that we'll look at is it basically is a Lisp. It just has M expressions instead of S expressions. So what I mean by that is we have S expressions, in Clojure, a Lisp, we have parenthesized expression. The first thing, the head of that list, is like the function call, and then we have everything else as the arguments. So in here we'd have like a function, takes function foo, takes X and Y, returns A. Rough equivalent in Prolog would be, so this would be like an M expression, where the head, we have foo, and then there's parentheses come after, and then we list the things. And so, this is a pretty small change. It's, as you can see, it's kind of a pretty trivial syntax transform. One of the more important differences that we'll talk a bit more about is that in Prolog, we don't make functions that return values. We make predicates that bind arguments. So for now, we can kind of think of this as, okay, well, it's like x and y are input arguments, and then a would be the output argument. So you could, we'd have x and y be assigned values, and then a would have some value assigned to it as a result of calling this. That's not exactly, we'll talk more about that later, but that's kind of the core idea. So off the bat here, we have that this has this very uniform syntax. If you look at Prolog, it may not be obvious because it specifies a bunch of like operators, but they are all just syntactic sugar for M expressions. Any Prolog program you can express, instead of the kind of the normal way you'd see it, as just uniform M expressions. And so off the bat, uniform syntax gives us the ability to very easily write transformers. So Prolog has the equivalent of macros. They're honestly not used very often though. Like, I think like in Clojure, you tend not to actually need them a lot, but they're there, they're really powerful. There's also kind of a culture in Prolog of doing metacircular interpreters, like writing a Prolog program that interprets Prolog programs, which is a similar idea to macros, in some ways arguably more powerful, but kind of the basics of Prolog. The syntax is very Lisp-like. But what are kind of the important, interesting things about Prolog? So kind of the two core concepts in Prolog programs, or like in the Prolog runtime, I guess, would be this idea of backtracking and the idea of unification. So backtracking is super powerful. It's the idea that we don't really need to do conditions. We can just generate possible solutions, and then if we reach a contradiction, just go back to find another potential solution and just keep going back. And we'll look at kind of the consequences of that. You do really neat things, like it means your Prolog programs, you very rarely need explicit control flow, and things are almost always like unnested, like you never really end up with things indented very much at all. And unification, we'll look at, that's kind of like destructuring, just even more enhanced and able to work in both directions. So let's take a look in a little more detail at these things. So talking about control flow, so Clojure's control flow, we can operate that on a pretty high level. We have, sure, our if and when and even cond, but a lot of the times we can operate on, a higher level of abstraction using things like map and filter and reduce to just, kind of abstract away the idea of even loops and conditionals in loops. So Clojure's control flow is quite powerful, but my thesis here is that that is still less powerful than Prolog's backtracking ability. So let's look at a little example of that. So we have this simple little Clojure program where we have some sequence, 1, 2, 3, 4, 5. We filter all the things that are less than 3, and then we map +2 over them. So pretty simple, pretty high level, right? We're just apply this thing to this list. We're not really worrying about the order of things. There is like an implicit thing that we're operating on a sequence, saying do this to the sequence and then do that to the sequence. Well, let's look at the Prolog equivalent, where what we're doing here is we have this predicate member, and we say, essentially what it's saying is say, okay, well, x is a member of 1, 2, 3, 4, 5, and x is less than 3, and y is x plus 2. And what this program will do, instead of giving like a list of, in this case, we'd end up with sort of the Clojure program will give us the list 3, 4. What this does is yields multiple solutions. So the first solution it yields is y is 3, and then we could either just say, okay, good, let's just go along with that, or I could say, hey, okay, well, give me another solution. And it says, okay, another solution is y is 4. And we could say any more solutions, and then say no, those are all the possible solutions. So the interesting thing to see here is that it's now completely separated generating candidates from how we test them, from what we do with the result. So in this case, we're using member to say give us all the members of the list, but we could change that function to be something else that would find all entries in a tree, read things from a file, do whatever, and the rest of the code stays exactly the same because it just knows you're giving me potential possible solutions. That could be reading an input, it could be getting things from network requests, but the code after that, completely uniform. Clojure is still pretty uniform because we have this sequence abstraction that works on a lot of things, but these things still are very much tied to the idea that they're operating on a sequence. So we go look at, maybe a more complex example where in Clojure we have nested lists, and so now it gets a bit uglier, and now we can see the amount of code that has to do with kind of the core of this, what we care about, this like checking that value is less than 3 and then adding 2 to it. It's now much more obscured by the additional stuff we have to do to traverse the data structure. Where the Prolog program, we change a little bit how we do the generation. Now we have these kind of nested, well, logically nested, but you can see in code still is like sequential, one after another, calls to member to set up these relationships. So say, okay, well, when XS is a member of this list of lists and X is a member of XS, then find all the places where X is less than 3 and Y is X plus 2. So the two lines to do the kind of the filtering and the addition, those stay exactly the same. We change a little bit how we generate candidates, but those are now completely separated. Maybe we could even say we've decomplected generating potential solutions with filtering with what we do with them. I think this is like a really powerful thing that is really kind of generally useful. This ability to separate how we generate potential solutions with what we do with them is a really useful concept to have in a lot of situations. So I think this difference, I hope, kind of convinces you that even Clojure is very high level, very powerful control flow. There's still other ways that we can do these sorts of things that can be even more powerful. So we talked about destructuring. Destructuring is great. We love destructuring things all the time. Very useful way of like pulling things out. No one wants to say, a get thing for or whatever. You just have your list, destructure on things. And so again, my thesis though is that is not quite as powerful as unification. So a little example. So say we have in Clojure, we have our map with the keys x1 and y2, z3. And we want to destructure it. So say, okay, I want to get x, y, z. And then in the case when z is 3, I want to return x plus 2. So, it's fairly straightforward. We have our destructuring step, and then our checking step, and then our like adding stuff together step. But the thing that I started to miss after doing Prolog for a while is in some ways kind of that when z equals 3 and that destructuring, those are both kind of ways where I'm doing the same thing. I'm saying, okay, well, I want to sort of make an assertion about the structure of T, right? I want to both be able to say, okay, these variables correspond to these values in that map, and also I want to assert that this value has some particular value. And in Prolog, this kind of rough equivalent we can express directly, where here I'm using a term with the functor T instead of a map. Prolog does have dictionaries, but for simplicity's sake, I'm just using kind of simple compound terms here. So kind of this is like the first line in the let, where the T is this thing with like 1, 2, 3. And now on the second line there, when I have our term lowercase t, and then I unify it with the uppercase T, where I say T and then xy3 equals the capital T. And so this is kind of the core. This is unifying the term, the term lowercase t with kind of two holes in it, and then one instantiated value, that 3. I'm saying, okay, now unify it with this t. And so in this case, that unifies and says, okay, well, this is true when x is 1 and y is 2. So it succeeds, it unifies, and then I can add them together. I can do this in one step. And if, say, we had like a 4 instead of a 3 in that position there, then the unification would fail, and this would just say false. So we can't unify this because we have a 3 here and a 4 there. Those are different things. We can't unify them. And so in this way, we can combine this pulling out values to destructure things with checking what the values are, kind of this one unified step. So if people have played around with Elixir, this might seem somewhat familiar there, which kind of Elixir has because of its Erlang heritage, which Erlang has because of its Prolog heritage. So if you like Elixir, maybe you should learn Prolog as well. Anyway, this is, I think, a very useful thing which you can do in unification. This ability to combine destructuring and testing is a really powerful idea that's really useful in lots of situations. It's one of these things that I really find myself missing now when I come back to Clojure, that like, okay, I destructure, now I also need to check those values are just destructured. Why can't I do this in one step? You can do even more than this with unification. Not to go into too much detail, but say here I want to both extract some values from a map and also add new values to it. So in this case, in the Clojure thing, I have one line to destructure, then I also have to do another assoc here to turn it as a vector. Presumably be doing something more complicated with it. Our kind of Prolog equivalent is actually even shorter, where I have T now as this thing with two holes in it, where like A and B just are variables that aren't filled in yet. And now I do this interesting thing where I unify this partially filled in data structure with another partially filled in data structure. And the unification algorithm says, okay, well, this succeeds when X is 1 and Y is 2 and A is 3 and B is 4. And now as a result of this, I have my variables X and Y are referring to those kind of keys in our T data structure. And now I've also set the A and B of our original T data structure, kind of in this one step. I've done things going in both directions. So really powerful idea, really useful concept in a lot of situations in Prolog. This kind of the power of that humble equals sign. You know, it's not just assignment, it's not just comparison, it's kind of both. And especially because not only is it just doing this one thing, it's also part of this implicit control flow, because if the unification fails, we'll backtrack and we'll find other possible solutions until it can unify. So really, really powerful concept that comes up in a lot of places and makes lots of things in Prolog just surprisingly, incredibly concise to do. So the final really cool thing I want to talk about from Prolog that I also miss a lot in other languages is the ability to have predicates run kind of in multiple directions. And probably we'd say to have like multi-moded predicates. The idea is, I talked earlier, kind of said, oh, it's kind of like we have a predicate where, you know, X and Y are input arguments and A is an output argument. But it turns out you don't really have to enforce one's input, one's output. They can kind of be whatever they need to be, depending on the context. So for example, in Clojure, we have a bunch of different functions for doing things with sequences. We can concat sequences together. We can take the first thing from a sequence. We can take the rest of a sequence. We can use this function from like core.math to combinatorics to get all the subsets of a sequence. And they're kind of related, but you know, they're separate functions, right? They're doing different things. But then let's look at the kind of the Prolog equivalents of these functions. So for concat, we have the predicate append, which we can see here. We're saying, okay, well, if the first thing is 1, 2, the second thing is 3, 4, then the third thing is going to be what those two things concatenated are. So in this case, it says, okay, well, this succeeds with C being 1, 2, 3, 4. We could also use this, though, to get the first thing from a list by saying, okay, well, what would it take if we append the list that has one element called X with something that we don't care what it is, and if we append those, the result is going to be the list 1, 2, 3, 4. And Prolog says, okay, well, this is true when X is 1, because we're saying append the list 1 to some value that I don't care about. The result is going to be the list 1, 2, 3, 4. Okay, well then X is going to be 1. So we can use that same append function, giving like different arguments, variables, and different arguments to values to get the first from a sequence. And so, may not surprise you to know we can also do the other thing here. We can use this to get the rest of it. We could even, if we wanted to, we could have combined this rest and the first together to get both first and rest in one step. There are easier ways of doing this, but you know, the point being. So we can see here, okay, we're able to use this same function, just kind of having different things be variables, different things be concrete values, to be able to replicate a bunch of these different built-in functions, or the Clojure would have these separate functions for each one. And we can even see that this more complicated subsets function can actually just be expressed with 2 calls to our append primitive here. Kind of puzzling out how this works, I'll maybe leave as an exercise to the listener. But it's pretty simple. This thing that is this function in another library on combinatorics and Clojure is actually trivially expressible as just 2 calls of this built-in predicate in Prolog. And the kind of difference being here, instead of a sequence of subsets, it returns multiple solutions. Then we can deal with those multiple solutions in different ways. So I really love this ability in Prolog to define functions that run in both directions. Maybe a little caveat, it's like you don't get this necessarily for free. Depending on what your function's doing, you may need to go your way to make it work in this way. Some things don't necessarily make sense to run in both directions, just based on what their arguments are. But I really love the ability to do this in some situations. I find it just really, really useful for a lot of things. So Prolog is great. I really like using it, but it's also not like the apex, right? There's still more things that we can improve and change and learn more from. One of the kind of interesting areas of research now is adding tabling to Prolog. Without going into too much detail with that, it's tabling, when I first saw it, like, oh, it's just like memoization in Clojure. But it turns out memoizing a language with logic variables and output variables that work in this way actually gives some like really interesting capabilities. So still more things to learn. Even if you know Prolog, you can still keep finding new interesting capabilities. So how do I bring this to Clojure though? We've learned these interesting things. What can we do with them now? So I mentioned core.logic. It's a cool thing, but for me, that's not really the core of what I want from Prolog. It's interesting, but I don't use Prolog to solve little mini can-run problems. I use it because of this pervasive ability for backtracking unification. Similar to, we talked about the power of immutability in Clojure, like immutable JS for JavaScript is nice, but it's not quite the same because it's just like, it's isolated, right? It's not part of the language as a whole. Something that I do find useful is, Datalog. Now, I'm super happy to be able to write Datalog because I realized, like, oh, this is like Prolog in a lot of ways. Not in all ways, it's not the same kind of unification and like writing all my code. It's not like the same kind of homoiconic stuff. But this power of backtracking, this ability to write very high-level queries is a really nice thing. So realizing, hey, I should take advantage of Datalog more when I'm writing Clojure. The great Specter library, something that for a long time just seemed like super overcomplicated to me. I've recently kind of fell in love with it, and I love using Specter on all sorts of things now. I think part of it was realizing that there's kind of this equivalence from our Specter, kind of our selectors, like the path navigators, and they have like a pretty close analog to Prolog predicates, so kind of repeatedly filtering these possible solutions to these things and then saying, give me all solutions or give me just the first solution. So one of these things where learning something in Prolog made me appreciate something that existed in Clojure that much more. It's made me kind of think of some other interesting things we could do with Clojure. Like I find backtracking an incredibly useful thing to have in Prolog. Could we bring backtracking to Clojure? We might have to do it in some kind of more restricted way, but just seeing how much it simplifies control flow for so many things is incredibly useful. One of my favorite Prolog features that we didn't really have time to get into is this thing called DCGs, or definite clause grammars, and essentially with like the tiniest little bit of macros, you end up in Prolog get the ability to write parsers, like just as easily as you could write regular expressions, but they're like full-on parsers. They're much more powerful. And a big part of it is because of the backtracking you get in Prolog makes it extremely easy to write kind of these generalized parsers. And I wish I had that in Clojure. So now I'm thinking, is there a way we can kind of bring, like the AMB operator, some ability to add backtracking in Clojure? Specs are kind of a thing that's like, well, I don't really like types. Specs are kind of like that, but what really do they do for me? Thinking more about unification has made me think a lot more about specs from a different point of view, of saying, can we use specs to both check and coerce, like transform things, somewhat analogously to how we do unification in Prolog. So now I'm thinking more about how can I take advantage of spec to give me the same kind of power that I love in Prolog. So I hope that people have found this interesting, maybe inspiring. I hope people go out and want to learn a new thing. I'd recommend Prolog. I think Prolog's really fun. But as long as it's something new, I think just, try to never stop growing, right? Always try to find something new that you can learn, look at new things from an existing light, and just always try to be better. So thank you very much for watching. I hope you enjoyed. Have a good day.